All right. And so, yeah, so we'll go right into questions and such. So just a quick reminder again, is that this week we'll continue linear regression, which is section like 19 and 20. So the idea is that we'll go over concepts, most of section 19 today, and then into tomorrow, section 20, we'll also kind of talk about maybe some of the sections, the material from section 19. So we might talk about some other stuff deeper into context, especially as you guys get some practice actually going through that section. But then we'll talk about extensions. And then next week, which will be Tuesday's study group, right? We'll actually, I think what we'll do is we'll go actually do section 17's Bayesian statistics, since that was something we skipped over, but I felt it was a better idea to introduce you guys to linear regression now, and then give you guys a little bit extra time to kind of digest that, since that's going to be the main focus of the project. And I realized too, so one thing I put out on the Slack earlier was pair programming. So I'm just gonna share my screen because then I can talk about it and then we'll go into questions. But talked about pair programming. Sorry, I moved my person. There it goes. Okay, so pair programming. So I know a few people. You can see 5 responses already. I'm actually surprised only 5 people. So if you haven't seen this yet, you know, I shared it on Slack, right? I can send it out again maybe after after study group. But if you would like to participate in a pair programming activity, it's been a while since we've like done a formal one. I think this would be great. I think in groups of like maybe 2, at most 4, but I'm thinking 2 to 3 people. And the reason why I'm asking is just seeing like people's like timing preferences and timing availability. That way you guys can actually, you know, pair up in a, you know, reasonable way. I know, for example, hopefully people don't mind me calling out. I know Mike has done it. I know Andy has done it. I know Christine has done it. I think Nadine, yeah, Nadine also did it. So I know some people here, you know, who haven't submitted that form. If you really don't want to do it, I'm not going to tell you to go, you know, do a pair programming activity, but I would highly suggest it, since I'll introduce it tomorrow, as well as groups, we'll give you guys some more time. The idea is that you guys would practice together doing a linear regression project, like a very small one, and we'll time limit it too. That way you guys don't have to worry about like having this interfere with your actual project that you'll be doing. I think it's a good opportunity, and we'll talk more detail about it next time. But just give me a thumbs up. Are you guys interested in doing pair programming activities, like as a group kind of thing? Give me some thumbs up. All right, cool. So again, I know a couple of people came in. I think Stephen, Jessica, you guys came in. The link is on Slack, right? Please respond by end of today would be amazing, because then I can actually make groups, everything like that. And then we'll talk about how you guys, what the activity is tomorrow. Okay, sound good? Awesome. All right, so with that business on the way, we'll go straight into questions. So let's hear. So there's quite a lot of questions, which is awesome. I don't know if it's the same person or different people, whatever, but I think they're all very relevant, especially focusing on section 18 and then section 19, which some of this we'll actually talk about probably today in our actual study group, but it's good to go over it. So first thing was these 2 questions, in particular, the JB test, which I don't remember exactly what the abbreviation stands for, but the JB test is done on sales versus TV, so making a linear model with simple linear regression, so just 2 variables. And they talk about normality. So I'm assuming normality, when they're talking about like the residuals, right? We always check the residuals for normality and stuff like that. Basically, you want to make sure that your residuals are normally distributed with a constant variance, essentially. So I think the question goes basically, they did a JB test, which is a hypothesis test for normality. And then someone says, you know, how do we interpret these results? I don't think the lesson is very clear. Well, that's fair enough, right? Sometimes it can be kind of confusing exactly how they want to do this. So Jark, yeah, I don't know, I'm not French. I didn't study French either. So people who pronounce this, JB tests. So with the JB tests, it's like you will find that there are many different statistical tests to test for normality. And this is where, you know, I don't think we have too many people who are very like a heavy statistical background, which is good because I'll probably start making them cry, is that people say like, okay, how do I interpret this stuff? And this is where like, you can see this probability, right? Basically this probability is very, very small, right? Meaning that like, okay, like it likely, in this case, I think, let's see, I think I want to make sure I get this. Try to reject the null hypothesis for normality. So I believe this is saying, if I remember this right, is that they are rejecting that as normal. Is that correct? Does anyone remember this particular lesson? Okay, I see a little nod, I think. So, and looking at this, I'm trying to remember the specifics. See, this is where I haven't memorized all lessons. But let's see here. The test is usually the largest because of other key plots are more reliable for some size very large. So I'm trying to think exactly what this is, but I believe this rejects the normality. Is that it's saying that it's not normal. Is that correct? Does anyone remember? Okay, cool. So one thing to note is that this is where you have to kind of make a decision where what makes the most sense. And this is, again, so for example, using hypothesis tests, right? And we can reject our null hypothesis, right? There's kind of some issue with that when you think about it, right? One is that if we reject the null hypothesis like this, it means that there's a chance that we have actually a false, a false positive, right? We're possibly not, and that's where hopefully we haven't had that, but it could be a consideration. This is where also like the curriculum kind of mentions that QQ plots are really great. Visually, you can see here, for example, I think they have the density, like the histograms next to it. If you guys recall, I'm not sure if that's what I'm interpreting this correctly, but I'm assuming that's what we're looking at, is that if your residuals clearly do not look normal, so for example, like you have something weird like this, or this one has a high kurtosis on the side right here, you might say, you know what, like we can't reliably do this. One solution to this, like, okay, let's say you say your QQ plots, it doesn't look normal. Maybe you do a statistical test just to double check to see like, does this work? Or if you have many, many, many points, you can't just simply use a graphical representation of your QQ plot because basically things start blending together. You can do some visual stuff, for example, like changing your alpha. So it's a little bit easier to see like where they're clustered around. But let's say you go with this hypothesis test and you find that they're not normal. The next step basically would be, well, one of two things. One is that you say, okay, I can't use this model at all for linear regression. It needs to be something different. And you have to use a different kind of model. So not linear regression. Another solution is doing transformations, which I think is talked about in section 19, if I remember that's right. So they do transformations. And this is a very common way to basically beat heteroscedasticity in like the residuals, right? Is that basically if your residuals are not homeoscedastic, you can use a transformation to hopefully, basically, I like to think of it like punishing the very large values and squeezing out the other values. And sometimes it still will be fine. And other times, the third kind of option, which is kind of like, I don't know, taboo to talk about, you just do that, you use it to make predictions anyway. And you have to reason to say like, is it fine to do that? Like in a strictly statistical way, you really shouldn't. But if you're doing this like linear regression, like you'll notice most data scientists, or even machine learning engineers, if you see linear regression, usually you'll see people not even check the like at least kind of like it seems very hand wavy, like we're like, oh, just they don't never do like a hypothesis test for the residuals. And the reason why is because we have other tools at our disposal as well. So even if we can't use a linear regression, it might be good enough to compare at least what would this linear regression look like compared to maybe some other advanced models. I say advanced models, but like other machine learning models. So basically in short is that at this point, like if you were to reject the null hypothesis, oh, it's not normal, you basically really should be careful how you proceed. You can proceed, but know that basically your linear regression test or model might not be a good description of this actual data, right? And you can either, transform the data, transform them so basically you get into something that's linear. It might be harder to interpret, but at least then you would have the assumptions filled for linear regression. Or in the extreme case, you basically say, can't use this data, which usually that's not what we do. Usually instead we say, well, we can't use linear regression, we'll use a different model. And the third option is really you proceed forward, but proceed with caution and just know that your linear regression might not be descriptive and you might be worth looking at other models that would do a better job. Okay, cool. I don't know who asked this question, but that seemed to gel well with you guys. You guys have any follow-up questions off anything I said? No? Okay, cool. Yeah, and this is where like, I'm not a statistic. For the record, I'm not a PhD in statistics, right? So I couldn't tell you exactly, like what the exact practice in PhD world is, but in a lot of ways, sometimes the industry world has to kind of move forward and you kind of say, you know what, we're going to just look at it and just move on and just keep a note on it. A good data scientist, even if you do perceive something and you're technically breaking assumptions, which for the record, we break assumptions, even statisticians will break assumptions. If their assumptions break down, you have to be aware of that and say, you know, are we okay to proceed or do we proceed in a different way? So documenting is a good place. The worst thing you can do is try to cover it up. Do not try to cover up these things because it's going to bite you in the butt later on, right? So just be aware of that. Cool. All right. So I think this next one, if I remember this right, similar, but I think it's a little bit different. So this GQ test, right? Residuals look very heteroscedastic, but the GQ test failed to reject the null hypothesis of homoscedasticity. So this is where like it looks normal for the residuals, if I'm hearing this right. Oh no, they looked very, visually looked very heteroscedastic, but failed to reject the null hypothesis of homoscedasticity. So maybe we should check out this lesson. We do the GQ, so I'm guessing this is what they're talking about, or oh, this was the same lesson, wasn't it? I mean, they're talking about these residuals. I don't know if anyone who wrote the question is here, so I'm guessing this is what they're talking about here. And this is kind of similar to the one that we saw, like in the example with the like when I introduced linear regression, right? So we got this like horn right here, and so they find, yeah, their GQ test finds that the p-value, they failed to reject it, right? So it isn't quite normal. The null hypothesis for homoscedasticity is the larger, more evidence we will have against homoscedasticity assumption, and the likely we will have heteroscedasticity, right? So the p-value for a test tells you whether or not to reject the null hypothesis, blah, blah, blah. So we say that even though we visually expect heteroscedasticity previously, we cannot be confirmed by GQ tests. So this is where we're talking about like it looks homoscedastic, but the test instead says like, oh no, like I can't like reject this null hypothesis, right? And remember, we always say we reject or fail to like reject or fail to reject. So in this case, you have to really decide, does it make sense? And I would say this is where I am someone who will say you should visually confirm versus going off of pure tests. Like if you think about it, if you went off of just a GQ test or even JB test, right, and you have the value, you can have the value in there and just to proceed forward. But you have to be aware, like, I think it's one of those things where it's worth visually inspecting, because one solution to this, and we got a solution like this doesn't look this doesn't look homoscedastic, right? Like it's definitely got some difference in the variance as we increase in TV, right, value. What could be a solution to this? People who've maybe gone through maybe section 19, what could we possibly do? If you just give up? Yeah. There we go.
Transform the data.
Transform data, right? So this is basically one thing we could do. It's like, well, maybe, for example, we can do a log transform of this. And so a log transform will punish, like a log transform or a square root transform does very similar stuff. Basically punishes these, like I say punish, basically lowers these very large values. So those differences will be very smaller. And in fact, I know this data set pretty well. This data set, if you do a log transform for basically its target value, you will actually see that this ends up being relatively normal residuals on your models and stuff. Basically, it's because these more extreme values, which, you know, this is the residuals, but like the residuals will follow from the actual target. It will punish those larger values and basically make more into like, think of like a rectangular shape versus this shape, which means normally distributed. In that case, probably that's a better visual. But like this test by itself isn't going to tell you that. Does that make sense? Like it's going to just tell you it rejects or failed to reject. JB test, maybe even it's, even though it gives you more information, for example, the skewness and the kurtosis, I still am not a big fan of like giving specific values for skewness and kurtosis, because it makes it feel more specific than you really can say, if that makes sense. Like these values, for example, like giving a t statistic, like we can give a t statistic and we know bigger is better, you know, or, you know, whatever you want to phrase that, but it doesn't tell you specifically what's going on. And skewness and kurtosis, we can actually visually kind of confirm a lot of this stuff. And you can say, oh yeah, there's definitely some extra pattern in there. So this is where plotting out your residuals in particular, or plotting out things, you can say, whoa, look at this. Like, you know, it seems to be increasing, this kind of like horn looking thing. We can use a log transformation to scrunch that down. Does that make sense to people? Yeah, I know this kind of sometimes feels very like I don't know, hand wavy, right? Kind of like, oh, you just kind of do this stuff. But these are kind of things too, like you get aware of and you test out things and see how well it performs too. But being aware, like always proceed with caution. But log transform in particular is very, very common when you're doing linear regression. Okay. Cool. So basically, if you do a hypothesis test and it basically disagrees with maybe what you visually show, think if visually, can you do something to transform this data, right? I would say even visually looking at this, I'm like, yeah, these don't look normal. I would not proceed forward. I don't care what the test tells me. Like I would say like, this might not be good enough. I would try to transform and see if it does better. Cool. All right, I know there's a lot of questions. I'm going to try to go through them a little quicker then. Let's see here. S18, when creating specific X values and predicting the Y values to plot the regression line, is there a reason to use min-max? Okay, so this is a type of transformation, right, of data. So min-max scaling. Surely we could use any 2 points, find the predicted values and plot through them. So they talked about like the Boston housing data that's in here, and they're using the min-max value. I think they're trying to show too. Yeah. So like they're saying like why use min max value versus something else. So I will tell you basically for linear regression, you don't really need to worry too much about scaling. Linear regression will kind of basically work regardless if you're scaling. Now there's some caveats to that too. Like it's might be easier to interpret and easier for you to visualize if you do like your different scaling, whether it's min max or normalized scaling or something along those lines. For other machine learning algorithms, some machine learning algorithms are required essentially to have smaller values. For example, a value between -1 and 1, or between 0 and 1, depending on the algorithm. Linear regression doesn't really have this issue. Linear regression kind of just like, all right, cool, let me just proceed. But for example, like neural networks, which will be much later in the course, if you have large values, basically you will never get to the answer. The answer won't get to it quick enough. So yeah. Someone have a question?
No, I was just going to say logistic regression also.
Yeah, logistic regression is another kind of way. Logistic regression is related to linear regression, which is kind of interesting. We're doing linear regression on the logistics, which will be next module, which will be fun. But yes, so I think the curriculum kind of introduces min-max scaling and different kinds of scaling because it's very common at that stage where you're doing the modeling. That's where you do it. But it's actually not required for linear regression. It can kind of help you get a better picture and a better visual of like what's going on, but your linear regression will still work regardless of this min-max scaling. Okay, cool. And you can think of this as like, it's going to squeeze things down or like, inflate it or however, it's going to do it. So it's still going to keep the shape, right? So your residuals will still remain the same essentially, but at least the percent change in the residuals will remain the same. Log transformation is going to be different because log is going to work differently on certain values, like smaller values than bigger values. Okay, cool. All right. So I'll move on then. So conceptually explain the QQ plot. Ooh, this will be a fun one. Here, tell you what, I want to make sure I have enough time to explain this. I'm just going to skip over it for a second because I see how to choose which scaling feeds transformation and form. Standardization, mean normalization, min-max. Like I said, it really depends on like the algorithms. Some algorithms, the way you determine the best fit is highly dependent on the scaling of the actual values. And sometimes you need the values between like 0 and 1 or -1 and 1 in order for it to effectively find the correct answer or correct model, I should say. Or I should say the best model versus the correct model. So in general, though, I don't know. I'm not a huge fan. I say some people like to transform the data so that every value is between 0 and 1 or -1 and 1. I'm kind of someone who likes to keep the data as little transformed as possible and only use transformations as needed for that algorithm. That way it's easier for me to interpret the model versus like if I min-max everything, it's a lot harder for me to like pull out the information, though it's possible. It's just a little bit more difficult. Okay. All right, so I'm going to take some time. Let's hear. I'm going to keep these. Let's see here. I think I'm going to keep these for a little bit later if we have time. But I want to talk about QQ plots because that's something from section 18. But we're going to talk about categorical variables, maybe multicollinearity. Maybe we'll talk about stepwise selection, but I'm going to keep these because we definitely will have time to talk about them next time, if not today. But okay, QQ plots. So QQ plots, I'm going to do a little drawing here. Where's my little drawing tool? There it is. QQ plots are one of those things where it's like people look at it and they're like, I can see like what it's trying to say, like, oh, is it normal, is it not? But like, how did we get here? Is that kind of more or less people's feeling on QQ plots? That's classically what I've seen a lot of people react to. So if you guys remember, a QQ plot looks usually something like this. Like we have, I'm just going to draw a line. It like looks something like this. And then we have like another line. I should probably use better colors, but that's okay. We have another line like that goes like through here. And so the idea is there is that if it's more normal, it should land on this, you know, light blue line right here. It should be landing, the point should be landing on here. And then, you know, there's some axes here, right? Like, I don't know. I don't even know what, Seaborn, or not Seaborn, the different packages put out there because it doesn't actually matter that much. So the real question, I think, from that question is like, okay, what's going on here? Like, how is this even being generated? Jessica, you have a question? Or
I think it
comment?
says on the X, it says like theoretical quantiles, and on the Y, it's like sample quantiles.
Okay, yeah. So theoretical, yeah, we'll talk about. So theoretical versus samples. And that will, yeah, I didn't even remember how it like labeled it because in general, it doesn't really matter. The scaling doesn't actually matter that much, funny enough. So QQ plots, usually we're talking about it in the curriculum in context of normality, right? Saying is it part of a normal distribution? And QQ plots are actually stand for, does anyone know what they stand for?
I think
Quantile.
Yeah. That's it. Yeah, quantile. So quantile. And so what this is really doing is that let's say you have a data distribution or say a data that look like, let's say this is just 0. So it makes it nice and easy for us to, and we have a data point right here, data point right here, data point right here, and data point like right here. Okay, so that's our actual sample. Obviously, you'd have a lot more than this, but some data is distributed this way. What we're basically trying to do with a QQ plot is we're saying, hey, let's take a distribution. In this case, let's say the normal distribution. So there's my nice normal Gaussian curve. Beautiful, right? All right. So what we do here with our for a QQ plot, we basically say, okay, each point is going to represent a quantile. So a quantile, remember, is just basically a separation of the data. Okay, so in this case, we technically have quartiles since there's 4, but like you could have basically separation. And then what we say, okay, let's pretend we see like, oh, we have 4 data points, so we should have 4 quantiles. Okay, so say 4 quantiles. I'll say 4Q. Okay, then what we do, we take our distribution, and depending on the distribution, we can use any distribution we want, but in this case, we're talking about normal distribution. And we split up this distribution into 4 equal sections. So each area underneath the curve will be the equal area. So I'm not going to do the best job here, but you can kind of imagine like it's not going to split perfectly between these two parts. It's going to be kind of like a little bit, maybe like right here. So this is like my first quartile or quantile, my second quantile, and then I'll have another cut right here. Let's say it's like about, it shouldn't be symmetric, so it's like about here, but my drawing's not symmetric since I'm not an artist, especially with a mouse. Okay, so you can imagine there, these are our 4 different quantiles, right? Or quartiles in this case. And so the idea here is that this would happen, you know, let's say this is at 0, right? And then it goes out. It doesn't really met the scale of this thing, but like, okay, it goes out. And so what we do here, we have our plot. And our plot, like Jessica had mentioned on the plot, it says like samples. Sample, and then I'll just put like TH for theoretical. And what we do basically, we go across this guy and say, okay, at this point, let's say this is like at 3. Or let's start with minus 2 over here. We basically go up this guy's like, oh, this is -2. And that's where the sample goes. I say, okay, and then we have a point over here. Let's say this is represented for this quantile right here. Let's say that's, I don't know, -1.5. I say, okay, -1.5. We make a little dot right here where that intersection is. Okay, so each dot's going to represent where this is going. And then we say, okay, we go to the next quantile over, right? And say like, oh, there's like 0 or something like that. And then we say, okay, that's 0 here. So like so far away over here. And basically what we do, we pair up each quantile with the other part. Okay, so we're basically matching up that quantile with our data point. And that's where we get these different data points on here. So, oops, sorry. My mouse going everywhere. So we have our data points. And basically we just keep going through that. And so if they're normally distributed, what you'll see is basically you have a straight line. Well, in this case, with this distribution in particular. Okay. And so that's the idea where basically we're splitting up our distribution into equal amount of parts that represent this part. So the idea, you can kind of imagine this, is that if we were to say, okay, this point right here should be on the average of this point right here. So like you would find that it would land here most of the time. If it perfectly landed on like what we'd expect it to be in that quantile, it will be perfectly on that line. But sometimes it'll be a little above, sometimes it'll be a little below, assuming it's the actual distribution. And so what happens is that, for example, if it's mostly on this line here, it's actually on that distribution. Or it seems to be related to that distribution. And what's kind of cool about this is that you can actually use any distribution you want. You can actually use like a uniform distribution. And everyone knows what a uniform distribution looks like, right? It just goes a straight line like this, right? So like you can literally split this up into equal spots, right? We can say like that's our quantile, our quantile, our quantile, our quantile. So there's equal areas and we can compare it. We can even have a different data set. Let's say like a different data set has different number of samples, right? And you can basically use that data samples to bake your own distribution. See, this data samples actually belong to this data set. And basically all you have to do is just essentially say, okay, here's my theoretical part. And you just go across where those lines, quantiles would exist. And then you do the same thing where you actually measured your sample. So each point on here on the y-axis would be a literal like value from the sample itself. And this would be kind of like saying, well, if it was part of a normal distribution, where would those values exist at? Okay. Does that kind of put a little bit better picture? Thumbs up, thumbs down, sideways. See some sideways over here. Yeah, kind of. Yeah, I know it's kind of funky because it's like, how does this actually happen? But the main thing to know is that basically, first of all, the axes, the scaling doesn't matter, right? And all we're essentially doing is we're taking a distribution, let's say a normal distribution, and we're saying we're splitting up this distribution to be equally likely in each of these quantiles. Basically, each of these sample points should have an equal amount of probability if they were centered around that specific quantile. Does that make sense? Okay, so the idea is that we're saying that each data point is equally, like you can almost imagine like this data point that exists here, if we did many, like we pretend like, oh, we did many other experiments, we would find like some of the values over here, like centered around what would be the typical value right here. And that typical value would be like represented here in this quantile of the histogram. And so we imagine like this is the quantile of this data point. And so what we're trying to say is like we're basically forcing and saying, well, okay, we pretend these sample data points are like exactly generated as if they were generated from a histogram. That's essentially what we're comparing. But all we do essentially is just list these data points on here, and then we match them up with where we would expect that quantile to be on the distribution. Is that, I know, like I don't know if I've explained that any better the second time around. But the short answer of like trying to understand what this is basically you're just matching up the distribution and your sample. And you can just simply do that by saying, okay, we're going to say each data point is equally likely in its own quantile. And then we create quantiles in the distribution that we care about, and we just match them up. So if they actually are from those distributions, you would expect a perfectly straight line. If they weren't, obviously real life, right? It's not going to be exactly in there. It's randomly, distributed inside these quantiles. But if it's not, you would expect some would be above, some would be below, but it'd be more or less kind of like almost like, what we expect like with linear regression. So we expect something that looks like that, and hopefully, if there's many points, it'd be very, very close. And it's usually pretty obvious from large data points is that if you have something like heavy tails, for example, sometimes you look like that, right? And it's like, oh, that's not quite normal. normal. And it'll never be quite normal, right? Like it's going to be slightly off, but the closer it is to that line, the better. Okay, cool. Yeah, any follow-up questions? Anything I can maybe clarify more?
If you were to draw two normal lines, I mean, two normal distributions,
Mhm.
one that goes across the X and one that goes across the Y,
Mhm.
and then try to match the quantiles that way. That'll give you a straight line, right?
Yeah. Mhm.
Is that basically what they're doing?
More or less, yeah, kind of, except that I guess in a sense, we're assuming the data points, let's see here if I can get this right, is we're assuming the data points are represented of of a normal distribution. So like maybe it helps if I say like if I had a normal distribution like this, and then I were to randomly pick values from a normal distribution, you would expect most values, right, to be like over here. And then every once in a while over here, right? The thing is, like, we don't have, like, you can imagine, we don't have this guy. So then what we do is say, okay, like, well, let's say we had, I'm gonna write this in red, we had another, I should have written this sideways, put on the y-axis. I'm just gonna redo this real quick. So imagine, again, I can't get my tool to work. Sorry, everyone. There we go. So we have our data point right here. Pretend this is like the real distribution that it was generated from. We have a few points that are kind of closer to here. And then once I'll be out right here. And then we say, okay, like our red is our theoretical down here. It's like, well, I'm going to draw upside down, but you guys get the idea, hopefully. It's like, okay, well, we have 1, 2, 3, 4, 5 points, right? Well, if we did this right, we'd expect, most points to be like in here, and then some over here. Is that even 5? I think that's 5. Yeah. And so what would happen is like, okay, well, this first point, we'd expect it to be, on the far left, if you flipped it over, right, would be over here. So we would say, okay, like if you imagine this as the axis, right? It's not the best way I drew it, but you can imagine that's how it is. I have a point that's like, oh, like, well, this is the middle part. It would be like right here, right? And then you say, okay, this next part right here, well, that would be expected right here, right? And then this next part would be right here.
That's what I was trying to say.
Yeah. So you're essentially matching it up, and then you're basically generating pretend values that would be in this like equally spaced quantile, right? Because if this was equally spaced and we had a perfect, normal distribution pulled out from this, right? It would be like, oh, if we have split them to 5 spots, when you do 5 of them, you would expect 1 in each of those 5 spots, right? Now, obviously, you can think of this when it's randomly chosen. That's not true, but you can imagine like that's what you'd expect if you did many, many, many different points over time. The average would be right here. Does that help? Yeah. Give me a thumbs up, sideways, thumbs down. That was kind of tough, but yeah. And so hopefully that kind of helps. And then the extension of this is like you can make any distribution you want, right? Like this is always like, I drew this little distribution here on the left, but I could have easily just gotten rid of this, and those are data points. And I could have instead have a normal distribution. I could have like a uniform distribution or a Poisson distribution or whatever distribution you want. You can even define the distribution from another data set sample and actually compare those points as well. The point is that basically we're just comparing like where we'd expect these things to be. And if they're as expected, it'd be a straight line. Yeah, Jessica.
So it's like for each quantile of the sample data, we're plotting it versus the quantile of what it would be if it were normal.
Right.
Okay.
Yeah.
And so each little line there is a quantile.
Oops, I erased it, but yeah.
All right, I think I'm getting it.
Okay, cool. Yeah, I think it's one of those things where like, and honestly, like hopefully you guys come out of this like, oh, kind of get this a little better. But even if you didn't, like as long as straight line means, oh, it's on that distribution, you'd be pretty set. But it helps to know like how this was even formed. Okay, cool. All right, so let me go ahead and clear this guy. And like I mentioned, I think I'm going to just save these guys for a little bit later for next time. Okay, since we'll probably talk about this a bit today, we'll probably talk about this maybe tomorrow, or we'll make sure to go over it tomorrow if we don't talk about it today.